Okay. So our second presentation is going to be by Dr. Greg Collecutt. He is the principal GPU software developer at TwoFlow. He flew from Australia to be with us today. So let's give him a hand. And he's going to be presenting about a recommendation that's going to give on how to better capture the upstream water level increases due to bridge deck obstructions.
Okay. Thank you very much for coming, ladies and gentlemen. It's a pleasure to be here and a pleasure to talk with you all and to present this work to you. The three names we've got there is I've got myself with the other name on the title is Bo User. He is our TwoFlow US lead person here now. And the third person on there is Urs Bomer, who works with the Queensland Department of Transport. And I'll come back to Urs in a little bit, but he might be someone that you want to contact if this presentation actually generates your interest. I mean, obviously, all three of us will work, but I do point his name out because he was quite a contributor to the work. So, what's really this core problem here? That's probably going to go on to the next slide if I click it again. What have we gone and done? We've gone and stuck a bridge in a river. You know, that river used to work just fine before we put the bridge there, but now we're going to put the bridge there, and I think the graphics on that is probably just good enough to see that the water flowing from left to right, and the upstream side, the water level's higher than the downstream side. And that's going to be a problem for people that build their houses upstream, particularly if they build their houses close to the edge of a floodplain. In this case, the water level difference is about a foot. It's not a huge amount, but in some situations you might have a number of bridges. And that 1 foot plus another foot plus another foot, just depending upon the slope of the river and so on, it can start to add up and cause a problem. And I really have to thank Brian for introducing this yesterday. In one of his dot points in his keynote speech, he said, bridge afflux is a significant source of uncertainty in hydraulic modelling. So this is something we've been trying to address. Now this is where Urs Bomer comes in, because at the Department of Transport in Queensland, he regularly has to review models that have been performed, or results and modelling that's been performed by a consultant or a subcontractor, submitted to the Department of Transport to say, our flood model says that this bridge is going to work, and the Department of Transport, he looks at the model and says, well, your bridge, that's not right, those results are terrible. Whatever sub-model or mechanism you've put into the software to select that bridge setup is just plain wrong. And so there's a bit of a gap happening in terms of accepted best practice in industry and accepted parameters to use in the model for getting the bridge afflux right. There we go. Now, we've been talking about SRH2D, we've been talking about HEC-RAS2D, and TwoFlow has also got a 2D engine and a 1D engine, and we also have a 3D engine, but we'll focus on 2D and 1D. When you're doing 2D, everything is depth averaged. So it's pretty hard to represent a bridge, which is, you know, it's got very three-dimensional structure. And in 1D, of course, it's cross-section average, so you can also represent a bridge. You have to do some sort of sub-model in there in order to predict what the bridge losses are going to be. Different software packages have different sub-models, different mechanisms of implementing a bridge loss in the equations. And sometimes there's really very little, like I said on the previous slide, no published guidance on what the input parameters for that sub-model should be. As a result, it's easy for practitioners to get it wrong, to produce a model result that really is well removed from what's going to happen in practice. So really the whole purpose of this collaborative work with the Queensland Department of Transport is to publish a recommended model, at least for TwoFlow anyway, but you can probably implement this in other packages, and with some parameter guidance for that model. So to begin this work, why does it do that to me? I'll try, where's the page up? I'll try a right arrow, that'll do. Okay, too simple. So what we started with doing is Urs set up a two-dimensional model in the Flow 3D software package, which of course can also do 2D. But this isn't a plan form 2D, this is a vertical slice through the bridge deck. This is a common bridge construction in Queensland, as you'll see on a subsequent slide later on, where you have a solid concrete bridge deck, pre-tensioned, reinforced concrete, with some guardrails either side, a little bit of a crowning in the middle of the road. And so as you can see in this CFD model, we've got a wake behind the bridge, we've got a vena contractor underneath the bridge, we've got surface waves above the top of the bridge once it's completely overtopped, and we've got a head loss between upstream and downstream. Now, I'm just going to point out some nomenclature on this slide that is going to be important for you to have in your head during the graphs that I'm going to present. So the two variables on the left, we've got T and HB. HB is the height from the bed, the riverbed, up to the soffit of the deck, or the obvert, whichever word you want to use. And T is the bridge thickness of the deck from the soffit up to the top of the curb. It turns out that the ratio of those two is important. So in further slides, I'll be talking about the ratio of HB on T. The other variable that I'm going to talk about here is because in this 2D model we don't have any piers, we don't get any losses until the water level at least gets up to the soffit of the bridge. So the region of interest for the calculating the head loss is the water above the soffit of the bridge. So we're calling that tailwater. It's actually the downstream water level above the underneath of the deck. Not above the riverbed, but just from the deck, underneath of the deck upwards. So we ran a whole lot of 2D CFD models and calculated the head loss as a function of the tailwater. And what you can see there is the curves with the dotted lines have been done at a higher flow velocity of 10 feet per second. The curves with the solid lines have been done with a lower flow velocity. There's a common shape. All the 6 curves there have something in common in the way that the fluid is behaving as it flows past the bridge. You've got almost no loss when the tailwater is 0, and then it rises to a peak, and then it decays again afterwards. And the decay is quite slow, almost like a 1 on X type relationship after the peak, something like that. You can see that the magnitude of the peak is going to depend on the flow velocity, which is what you would expect. In fact, people who've got some CFD experience would say, okay, the magnitude of the peak is going to be a function of the flow velocity squared. And the other feature in this graph you can see is that the position of the peak varies a little bit to different tailwater levels. And it varies according to what the bridge deck thickness is. I should explain that in this case, for all the different bridge thicknesses we used, we adjusted HB to be 4 times whatever the bridge thickness was, because this ratio turns out to be an important number. So, can we non-dimensionalize this? Can we get to a generic shape curve out of that family of curves? And of course the answer is yes, or I wouldn't have said it. So what we do here is we normalize the tailwater with respect to the deck thickness. So this is tailwater on T, is the abscissa of the graph, and the ordinate up the y-axis now is the loss coefficient, which you can see the formation here when you've got your delta H is a loss coefficient times velocity squared on 2g. And what we can see there is now we've got a family of curves that have collapsed together into one fairly generic shape. The other important thing is when we rerun all of that modelling for different ratios of HB on T, then we find that the peak that it gets to, in this case the peak is around about 0.28 loss coefficient, and the tailwater on T ratio at which it occurs is around about 1.6. When we go to different ratios of HB on T, we've tried 2, 4 and 6, we find that the peak form loss coefficient varies. It increases as the bridge gets put lower down to the bed level, but the 1.6 T stays pretty constant. That seems to be quite fixed. So, we've got all this beautiful CFD modelling, but is anyone going to believe the CFD modelling? Particularly a simplified 2D model like that. You know, it'd be nice to actually have some real-world data. So this is the bridge we selected. This is a fair dinkum Queensland bridge. Okay, it's common as anything. The concrete deck, the guardrails, and in this case, this is a small bridge, so there's no piers underneath. It's just got concrete abutments either side on the riverbank, and then it's got I can't remember exactly, about a 3 or 4 metre clearance underneath for the riverbed underneath. So it's not a huge bridge, but it's big enough to get real-world data. It's also low enough down on a creek not far out of Brisbane that it's considered to have low immunity. In other words, it gets flooded all the time. Usually once a year it goes under. So the Moreton Bay Regional Council installed some flood sensors for us, some water gauge level sensors. These are pressure sensors. I don't believe they're measuring total energy. I think they're just measuring static pressure to give the water surface elevation. One upstream, one downstream of the bridge. And then we recorded data for about the recording system's been running for a couple of years, but we had a few teething problems with it, but we got it sorted out eventually. And in February 2022, we had a fantastic flood event in Brisbane. In fact, this river, Cedar Creek it's called actually, this creek, is in a relatively small catchment, but at the head of that catchment, we had over 3 foot of rain in 24 hours. You know, it just bucketed down. There were quite a bit of flooding in Brisbane itself as well. I mean, I don't think it was as bad as what happened in Kentucky recently, but it was still, it was quite significant. You can see in this chart here, we're plotting the upstream and downstream water levels as a function of time over a 3-day period. The orange dots are the upstream and the blue dots are the downstream. So you can see that when the chart first starts there, the water level's much the same, upstream, downstream, and then as it gets over the bridge, you get a delta water level from upstream to downstream. I've put a silhouette on the bridge there to indicate, whereabouts the water level is compared to the bridge. And in the plots further on, I'm going to turn things on the side, and I'm going to have the silhouette the other way around, if you can mentally do that. One of the first questions we asked ourselves, though, was how good is this data? The measured data, is it, I think in retrospect, it would have been nice to have 2 or 3 flood gauges upstream and downstream to get a little bit of better statistics on the distribution of water level. But at the moment, we've only got one, so that's all we've got to work with. So one way to assess that, this is going to sound completely back to front, but I just talked about we did 2D modelling, then we've instrumented a bridge to check the modelling. Now we're going to go back to modelling to check the instrumentation. So we ran 3D, beautiful big 3D CFD models of the bridge and the surrounds. We had a nice LiDAR scan of the bridge, of the area and the bathymetry, and a local survey scan of the bridge and the bathymetry under the bridge where the LiDAR didn't get to and everything. So it's good geometry. We ran it both in Flow 3D and in Open Foam. Flow 3D had the renormalisation group turbulence model, and Open Foam just used the standard K epsilon. And we ran a number of different flow rates with this, and so this is now plotting the expected delta H across the bridge as a function of the water level. And this is where I've turned the bridge on the side. So at 249 feet, that's the soffit of the deck, and then the bridge top, the top of the guardrails around about 254 feet. And you can see there that the CFD results, pretty good agreement with all the dots. The dots are the measured data. There's a lot of scatter in the dots. That will be because of swirling surface waves that go over the flood sensors, the gauge sensors, as well as there was some debris on the bridge. We didn't manage to get to it as soon as the water went down because someone else had already cleaned it all up. It was very kind of them, but also we couldn't see what the final debris state was. But just keep in mind that debris build-up on guardrails, you might assume that guardrails have got a porosity value of 75% or something, but things build up on them and they clog pretty quick. Yeah, I think that has contributed to the scatter, but pretty good result. Unfortunately, we didn't run the Open Foam to quite deep enough water levels to get the full shape of the curve there, but peak is probably captured and it looks about right. So the next step is to try and get this shape of curve, the up, the peak, the down again, and tail decay, into, as a sub-loss model into a 2D solver. So we, of course, writing 2Flow, we put it into the 2Flow HPC solver. It's implemented as a momentum source based on a head loss coefficient and whatever the structure velocity is at the bridge. Structure velocity is the actual unit flow divided by the depth less whatever solid fraction of bridge you have. So it's a fairly good indication of what the actual velocity is past the bridge, which will be a little bit more than upstream or downstream because of the blockage factor of the bridge. The model also has a blockage factor implemented on the cell faces so that you get reduced flux at the faces because of the presence of the bridge. But importantly, it also has the momentum source term in there as well. So we've got a three-step piecewise function in there. H1 is the depth of the height to the soffit of the deck. H2 is the height of the peak. Now remember I talked about the top of the peak being 1.6 times the deck thickness. So what we've implemented in there, the bottom equation there says H2 is H1 plus this expansion factor, F, which we've used as 1.6 times the thickness of the deck plus the solid fraction of the rails as well. And then for bridges that have got piers, you're going to have a form loss coefficient when the water level is below the deck, and then there's going to be this additional K2 component added from the deck and the guardrails, which is above. For this particular bridge, of course, there's no piers, so we just set K1 at 0, and then we set K2 at the 0.28 loss coefficient that we got out of the previous modelling. When we implement that in HPC, this is the result that we get. On the left is just a generic example image. I don't even know what depth and flow rate that was at. It was just a picture that shows the flow going over the bridge. It was completely over the topping the bridge in that case. And on the right is the loss curves that we get out of it as a function of the different water levels that we ran. So it's doing a pretty good job predicting the peak. I've got two curves there showing. The blue is for a coefficient of 0.28 and the orange is for 0.5. It looks like the 0.28 is probably a better fit than the 0.5. Bear in mind that a fairly significant component of that loss comes even just from the blockage factors of the bridge. Even if you omit the momentum loss term and just implement blockage factors on the faces, you'll still get a significant delta H, but that curve sits underneath the others. At high water levels, we seem to be missing the mark a little bit there. And I've got an inkling that that is possibly because at these high water levels where the flow is 10 feet above the top of the bridge, we've got a very interesting situation where the flow dynamics over the bridge is quite three-dimensional, and yet we're trying to solve this in 2D depth averaged equations. I think we're setting up some surface waves that probably aren't real, and that's contributing to making it look like we've probably got a localised peak behind the bridge and maybe, I don't know, I have concerns about that. But certainly when the water is peaking at the areas of maximum loss, we're getting it bang on. So I was happy with that. Those results do depend a little bit on the transverse velocity profile, which in turn depends upon your choice of eddy viscosity model for turbulence. The software is second order in spatial interpolation, so it does need eddy viscosity, or else you get quite fantastic swirls and eddies forming in your solution. And whether you choose the LES Smagorinsky model or whether you choose another one that we find that works quite well is the SWE turbulence model, which is basically it's a depth times friction velocity turbulence model. That one works very well as well, but depending upon which choice, you'll get some slight differences as well. But generally, we're pretty happy with that agreement. Another possible route to getting bridge afflux without going to full-blown CFD models with Flow3D or OpenFoam or Fluent or CFX or SAR CCM Plus, or there's probably 100 different commercial CFD packages out there. Another possible route is the 3D 2Flow engine as well. It's called, the HPC is actually a finite volume scheme, but this one for some reason was very particularly called 2Flow finite volume. It was developed by Ian Teakle in our group, and it's a full 3D engine. It uses the hydrostatic pressure assumption, so that's why it's not the same as CFD. But it can do a pretty good job. We've got this new structure loss module in there now where what you can do is you can find which of the mesh cells are shadowed by the obstruction of the bridge, and then you can pro-rata blockage factors and drag coefficient values into those cells. So you can see here we've got on the left plot we've got a transect curtain plot along the longitudinal flow path there, and you can see the presence of the bridge by that big blue blotch in the middle there where the water flow is near zero. And that, surprisingly, well, maybe not surprisingly, that actually gave pretty good results as well against the measured afflux of the bridge. Again, slightly different results depending upon which turbulence model you use, but it looks like, you know, the blue curve there with a drag coefficient of 1 and the Smagorinsky turbulence model is pretty much bang on. It's very good, particularly also at the high water levels as well, and that's what makes me think that, you know, to get the afflux once the bridge is really drowned out, if you want to nail that exactly, you probably need a 3D solver. So I've presented 2D CFD models of an idealised bridge. I've presented measured gauge data from a real bridge, 3D CFD models of the same bridge, and they all said the same thing. They showed the same generic loss curve that went up, peaked, and came down again with a long decaying tail. That curve is able to be collapsed non-dimensionally and a generic equation produced, and then you can implement that in a 2D solver, which is what we've done. Queensland Department of Transport and Main Roads is very, very eager to get consultants to be using this new model and just to use the coefficients that were provided in that table. Now, obviously, this is for people who use two-flow, which is very extensive in Australia, but quite a minor package over here in the US. And I've also presented some results from 3D structures in the two-flow 3D solver, which is called FE. Okay, thank you very much. Any questions? Yes, you'll have to excuse me. I am hard of hearing, so you'll have to use a nice loud voice.
I'll use my outside voice. Thank you for this presentation. I did have a question. You mentioned in your presentation debris and debris hanging up on the bridge rail or guardrail. When you go through this methodology with 3D modeling, let's say you were using this on the front end of the design, a new design for a new bridge. How would your method specifically, or does it specifically incorporate debris, and what assumptions would you be making if you were to do that?
Okay, so you're talking about running some 3D models. Are you thinking of CFD modelling for the bridge design?
Right.
Look, I think in that situation, if you're running a 3D CFD model, I would probably just block out the guardrails with a sheet, a solid sheet, so the water can't flow through them. It'll be a bit conservative, a little bit, but at least you'll get the full expected forces on the bridge from a structural design point of view at least. Yes?
I have two questions. One is, could you please repeat why did overflow do such a bad job versus Flow 3D?
A bad job? There we go. Look, well, what happened is we pretty much just ran out of time, and I ran a whole lot of open foam models up to a certain flow rate, and I had assumed that I had captured the full curve, but I botched it, and the maximum flow rate I used hadn't gone over the peak and down to the tail, and I didn't have time to run more. So that's what happened there. I mean, it's a slightly different result to Flow 3D, but at least the amount of data that is shown there, I think, is quite in agreement with the experimental data and the Flow 3D result. Yes?
Yeah, a question about more of the Department of Roads in Queensland. Are they requiring the 3D modeling in all the bridge sites, or is it more they're starting to look at it as something that needs to be done at site-specific? Is it something that's going to happen most of the places?
Yeah. No, I would say that they're for the large bridges that span the Brisbane River itself, so we're talking about 200 metre, 300 metre span bridges with many piers, or the Logan River, Yes, they are interested in seeing 3D modelling from consultants for what's happening around the piers and scour analysis and so on. For these little bridges on the little creeks, no, they're not interested in seeing 3D modelling for that, but they want the 2D model to have a reasonably realistic loss coefficient implementation and parameters used. And they're just tired of sending results back to us consultants and say, look, you really got this wrong. We can see that the bridge Afflux you've got here is it's just wrong, and you need to redo it. You know, that's what they're tired about. So by trying to introduce a common standard, I guess, or a best practice, at least for the 2D modelling for the small bridges. Yeah. Yes. Yes, I think there would be quite some interest in extending this work to look at larger bridges that have got girder subframes, different superstructure constructions, you know, train bridges, rail bridges. Yeah, there's probably a lot of intermediate design bridges that are larger and more complex than this little deck bridge that's on this creek that need to be studied and implemented as well. So I think we will find that the shape of the loss curve, I'd be surprised if it's a huge amount different. I mean, there'll be ways in which it's different, but I think we've got a good starting point to then look at, well, how does that need to be adjusted a little bit for different bridge designs? I hope that answers your question. So, yeah. Very good. With the orifice flow, so you're thinking about when the water level is above the soffit, but probably not quite above the deck. So you've got just this upstream, you've got the water hitting the edge and then going underneath with a vena contractor. Well, that's captured in the data. You can see there the grey dots in the region where the water level is hitting the deck, and it's just kind of a smooth transition curve up there. This model is not really, it's somewhat agnostic as to what the actual flow regime is at the bridge. It just implements a form loss coefficient as a function of the water level above the deck, and it actually seems to capture it pretty well. Yes, the flow regime will change as the water overtops, but it's